Why care about a strip of stitched fabric now? Because this is the kind of small part that has to behave predictably when everything else is moving fast. NASA's recent flight testing showed increasing variability in the behavior of reentry parachute energy modulators. These are textile devices that help absorb the sharp load that hits when a parachute deploys. If they work as intended, they reduce shock. If they do not, the load can move into places it should not. The concern is not just that a stitch breaks. It is that the break may happen in the wrong sequence under dynamic loading. That makes performance harder to predict. So, this story is really about control. How do engineers understand a failure path when the system is soft, woven, stitched, and loaded in a fraction of a second? An energy modulator, or REM, is designed to fail in a controlled way. NASA describes it as a textile mechanical device that dissipates snatch loads during parachute deployment. The basic structure is a long strip of structural Kevlar webbing, folded and stitched with a nylon's zigzag pattern to form what the article calls an emir. When the load rises above a threshold, the nylon stitches are supposed to rip. As they rip, the folded strip unfolds, and that motion absorbs energy. In the nominal case, this tear is orderly. The stitches go one after another, and the Kevlar webbing stays mostly intact. But NASA's flight tests have also shown anomalous cases. Some rows of nylon stitches are skipped during loading instead of tearing in sequence. When that happens, the surrounding Kevlar webbing can fail. That failure mode is called EM shredding. The hard part here is that the root cause is difficult to isolate with mechanical testing alone. NASA points to two reasons. First, fabric behavior is inherently unpredictable at small scales. Second, flight loading conditions can vary a lot. That means the same part may not fail the same way every time. To get closer to the mechanism, the team built a computational model at the fabric weave level using LS-DYNA. That is the key move in this study. Instead of treating the fabric as one bulk material, the model represents each thread of the Kevlar weave in each nylon stitch as individual 3D solid elements. That matters because the engineers are trying to understand to link failures at once how the nylon stitching tears, and how the Kevlar weave can start failing during shredding events. The goal is not spectacle. It is a clearer causal picture. NASA says the work had two main objectives. First, build a per-unit stitch model that captures the geometry and material behavior of the stitching pattern. Second, create a Python script that can duplicate that unit model along the full length of an emir. For the weave itself, the team used TextGen to create a 3D model of the Kevlar fabric. Then, with CAD software, they added nylon stitching passing through 2 layers of the Kevlar weave. The stitch pattern included a bobbin thread and a needle thread looping through the top and bottom layers and twisting together at the end of each stitch. The unit model was meshed in hypermesh using 3D tetrahedral solid elements. In LS-DYNA, the team defined elastic material behavior, contact, erosion for progressive failure, and boundary conditions intended to represent in-flight tensile loading scenarios. The article is careful about what the results mean. It does not claim the root cause is solved. It says the modeling approach was used to gain deeper insight into EM shredding, and that preliminary results supported the use of solid elements to capture the interaction between Kevlar and nylon threads. The Python duplication script also matters because it makes full-length and models easier to generate without building huge CAD assemblies. That improves workflow as much as science. If the model keeps proving useful, it could help engineers evaluate new EM design variations and compare failure behavior more systematically. NASA also notes a broader implication. This method could support other aerospace textile problems where weave level structure matters. So the larger lesson is simple. Sometimes the key question is not whether a material fails, but exactly how failure travels through a woven system.